Hello everyone, this is Dr. Webb. In the last video, we started talking about permutations. And so if you recall, a permutation on a set is a one-to-one and onto function from the set to itself. And the set of all permutations forms a group. And if our set is the numbers 1 through n, then that group is called Sn, which is the symmetric group. In this video, we're going to be thinking more about permutations, and specifically, we're going to be thinking about cycles that are inside of permutations. And so this will lead to cycle notation. So let's dive in and talk more explicitly about this. So here is a permutation, alpha. It's a permutation on the set 1 through 8. And if you look at this, well, what happens to 1? Well, looking at the permutation, 1 gets sent to 3. Then where does 3 get sent to? 3 gets sent to 6. And 6 gets sent to 1. So as part of this permutation, 1 is sent to 3, 3 is sent to 6, and 6 is sent to 1. And so we have this cycle of those 3 numbers in here. What about 2? Well, 2 goes to 5, and 5 goes back to 2. And so we have this cycle between the 2's and the 5's. The permutation swaps 2's and 5's. And then next we have 4's. 4 is getting sent to 8. And 8 is getting sent back to 4. So alpha also swaps the 4's and 8's. And last but not least, we have 7, and 7 gets sent back to itself. And so, in some sense, we can break this permutation down into these cycles. 1 goes to 3, goes to 6, which then goes back to 1. 2 goes to 5, which goes back to 2. 4 goes to 8, and 8 goes back to 4, and 7 gets sent to itself. Okay? And so the way that we can express that these cycles are happening inside the permutation is writing this permutation in what's called cycle notation. And so we can rewrite alpha in cycle notation. And the way we would write it is, well, you see, first we have this cycle. 1 goes to 3, which goes to 6. And then by putting the parentheses there, that means then 6 goes back to the first number. 2 gets sent to 5, ending the parentheses there, then says 5 goes back to 2. 4 gets sent to 8. So 8 then gets sent back to 4. And 7 just gets sent to itself. Okay? And so we sort of shorten this down. And if you notice, we have dropped off the 7 in the list. And sort of what mathematicians tend to do is if a number is a fixed point, so in this case, since 7 is sent to itself, it's a fixed point. We don't bother writing it down in the cycle notation. We just assume that any number that's not written there gets sent to itself by the permutation. Okay. So let's think specifically about a permutation that's just has a single cycle. And so in this permutation, alpha, the cycle 1 is A1 goes to A2, A2 goes to A3, all the way down to AK, and then AK at the end gets sent back to A1. And so since this has k numbers in the cycle, we're going to call this a k cycle. So k is talking about the number of different numbers inside of it. And so just to be clear about what this notation means, if I apply alpha to some I, and here we're thinking about I as being inside of 1, 2, up to n, where this is the permutation inside Sn. Well, so then what does alpha do? Well, if I is equal to something in the cycle, not in the last spot, then that number being AJ. So AJ in here, that's going to get sent to the next number in the cycle. So AJ gets sent to AJ plus 1. If we're in the last slot, is I is in fact AK, then the cycle is going to send it back to the beginning, to A1. And then if I is anything outside of the numbers inside this cycle, so if it's not equal to AJ for any of these in here, it's not going to do anything to it. And so alpha I there is just going to spit back I. Okay, and so this is what this notation means. This is how we can read this as a function. So when we have the numbers, say our cycle is 1, 4, 2, 5, that's our, so this would be a 4 cycle. Well, if I apply 1, 4, 2, 5 to the number 1, if I do 1 onto this, actually let's not put parentheses around it. I don't want you to think that that's a cycle of 1 being sent to itself. So this, by this I'm meaning plug 1 into, apply this permutation, this 4 cycle onto 1, well 1 gets sent to 4. If I do 1, 4, 2, 5, and apply it to 2, that gets sent to 5. 1, 4, 2, 5, applied to 5, so 5 is the last number, and so it sends it back to 1. And then if I applied it to something else, like 1, 4, 2, 5, applied to 3, 3 is not inside the cycle at all, and so the cycle leaves it alone. It spits back 3. Okay, so here's permutations back in the notation we were using in the last video for them, where it sort of lists out the domain and then where everything gets sent to underneath it. Let's rewrite this in cycle notation. Right. So let's start off with sigma. And so sigma here, it's easiest to kind of write these down one at a time, start with one number, and then go through the cycle that's involved in it. So in sigma, 1 gets sent to 3, 3 gets sent to 2, so we have 1 gets sent to 3, 3 gets sent to 2, 2 gets sent to 5, and 5 gets sent back to 1, the number we started off with, and so we close off that cycle. And then what's left in sigma, we haven't touched 4 yet, and 4 just gets sent to itself. And so we could put 4 here. We don't need to. We can leave this off. And leave the fixed point off. Okay. What about row? So row 1 gets sent to 2, 2 goes to 4, 4 goes to 3, 3 goes to 5, and then 5 goes to 1. And so we close that off. So row is just a single 5 cycle. We can think about sigma as just being a single 4 cycle because we're dropping off the 4 at the end, and it's just 1, 3, 2, 5. Okay, now what happens when we apply these to each other? So if we do row sigma, and so row is 1, 2, 4, 3, 5. Sigma is 1, 3, 2, 5. So we're going to think about this the exact same way as we did in the last video, where really sigma is being applied first, and then row is being applied second. And so I'm thinking about, for each of these numbers, I'm thinking about what happens to it. So let's start with 1. So 1 goes to 3, and what happens, so 1 applied to here would spit out 3, and so what happens to 3 in row? 3 gets sent to 5. And so 1 ended up getting sent to 5. Next, I'm going to concentrate on what 5 gets sent to. So 5 is at the end of sigma. So sigma sends 5 to 1, and then 1 in rho gets sent to 2. So overall, 5 gets sent to 1, and then to 2. Now let's focus on 2. So in sigma, 2 goes to 5, and then in rho, 5 gets sent back to 1. And so, since 1 was the first number in the cycle, we close this off. And so, our new permutation, rho sigma, has a cycle 1 goes to 5, goes to 2, and then 2 goes back to 1. Now, what numbers haven't we done yet? We haven't done 3 or 4, so let's focus on them. So in sigma, sigma sends 3 to 2, and then in rho, 2 is sent to 4. So 3 got sent to 4, and since these are both permutations on S5, and we used all 5 numbers, this should be it, but let's just double check that 4 gets sent back to 3. So 4 does not appear in sigma at all, so 4 is fixed by sigma, and so it just passes through, and then in rho, 4 gets sent to 3, as we expected. So rho sigma overall has 2 cycles. The 3 cycle, 1 gets sent to 5, which gets sent to 2, and then back to 1. And then the 2 cycle, 3 gets sent to 4, and 4 gets sent back to 3. And so we have written rho sigma in cycle notation. Okay, so the rest of this video we're going to focus on proving this big theorem that if we take any permutation in Sn, so sigma is a permutation on the set 1 through n, then we can represent sigma as a product of disjoint cycles. So disjoint here means the numbers that are in one cycle don't appear at all in any other cycle. So every number appears at most in one of the cycles. If it's a fixed point, it won't appear in any of the cycles because it'll just be in a cycle by itself. Okay? Much as we just represented rho sigma on the previous slide. Okay, and so we're not just going to go jump right into proving this. Let's start off with a couple of lemmas. So first lemma is we're going to let I be one of the numbers from 1 up to n. Then there's going to exist some minimal positive integer k such that sigma to the k, so applying sigma k times onto I, gives us back I, and that if we do it any less times, if we look at what happens to sigma 1, sigma 2, all the way up to sigma k minus 1 of I, all of those are going to be distinct. So no two of those equal each other for any L and M between 1 and k. In fact, that should be greater than or equal to 1k. Okay, so let's talk through why this lemma is true. So first thing we're going to think about is, let's just think of the list where I have I and then sigma I, and then I apply sigma again and get sigma squared I all the way as far out as you want to go. So think about doing this infinitely many times. Okay. Well, since sigma is a permutation on Sn, this set has to be contained inside the numbers 1 through n. Because it's a one-to-one and onto function from 1 to up to n to itself, when I look at the range of just applying sigma to I over and over again, I'm only going to be hitting numbers back through 1 through n. And so this is a finite list, and my list in the beginning was infinite, And so if I have an infinite list that actually is a subset of a finite list, that must mean that eventually I get a lot of things getting copied over and over again. Okay, so let's let sigma r I equal to sigma si represent the first time that a number gets copied. So this is minimal in the sense that sigma ri is the first number that appears twice, and sigma r is the first time that it appears, and sigma s is the second time that it appears. So r and s represent the first copy, sigma r is the first time that it appears, sigma s is the second time it appears. And so my big claim here is that r is actually 0, is that sigma r of I is equal to I. Okay? And I'm going to prove this by contradiction. So if not, and sigma r of I is some number other than I, well, then I can apply the inverse on both sides of this. And I can do sigma inverse on sigma r of I and sigma inverse on sigma s of I. Well, since these are equal, sigma is a permutation, so it has an inverse. What's the inverse going to do in the count? Well, if I take sigma r and then I undo one of the sigmas, this will actually give me sigma r minus 1 of I is equal to sigma s minus 1 of I. And so we've actually found a smaller occurrence where the two are equal, right? And so sigma r of I was actually not the first case in which they were the same. It actually happened at least once before. And so this gives us a contradiction that r and s are minimal. So this is contradicting that our choice of r and s was minimal. And we could do this so long as r was any number bigger than 0. If r was 1, we could still do this back and end up in the 0 spot. And so this establishes that this happened first, right at the beginning. So sigma r of I was I to begin with. And so then we have this sigma s. We're going to just define s to be k. Okay, and so this establishes the first part of the lemma. Now, what about the second part? Well, the second part just follows from what we proved. And so let's clean this up. Well, so we've just shown that I equals sigma to the ki. And again, remember this k, that's taking over for s. And this is the first repeat in our list. And so if it's the first repeat, that means that there can't be any other repeats before it. And so by being the first repeat, this gives us that sigma L of I can't be equal to sigma N of I if L and M are different and L is at least 1 and they're all smaller than K. Okay, and so these can't be the same anywhere before this if the first time things are repeated are at sigma K. So all the things before it are distinct. Okay, and so really deep down this is saying that if I take I, sigma of I, sigma squared of I, all the way up to, well, I know that when I get the sigma of k, I get I again. So let's stop one before this. Sigma k minus 1 of I. These are all distinct. Okay, so there's the lemma we just proved. Now, using this lemma, we are now going to use it to prove another lemma, which follows pretty quickly from our first one. And that's that, assuming that we have same notation as before, that for some I in there, we have the list I, sigma squared I, up to sigma k minus 1I, that these don't, there's no repetitions in there. And then, well, what this really means is that sigma contains the k cycle that goes through. 1 gets sent to sigma I gets sent to sigma squared I, up to sigma k minus 1. And so this really just follows immediately from the previous lemma. And it's pretty much from definition, because I is getting sent to sigma I. Where's sigma I getting sent to? Sigma squared I. And we can just keep this cycle going around until once we get to sigma k minus 1I, well, sigma ki is I, and so sigma k minus 1I gets sent to I. And so this is coming from the fact that I is equal to sigma ki. And this is a legitimate cycle because, as we saw in the previous one, all of these elements in this cycle are all distinct from each other until we get to sigma k, which gets us back to I. So this is a legitimate k cycle. Okay, now let's go back and prove the theorem. So we have same idea, same notation as before. Now we want to show that we can represent sigma as a product of disjoint cycles. Okay, and so the idea here is first we're going to apply the lemmas to, say, 1. We just have to pick a number. We might as well pick 1. And so then that gives us some cycle, 1, sigma of 1, sigma squared of 1, all the way down to sigma to the k minus 1 in there. Okay, and then we look at that list. So that's giving us some of the numbers from 1 to n. But maybe not all of them. And so if there's some number missed there, so let's then so second, we're going to take sort of the minimal a in 1 through n, but then we're taking out 1, sigma 1, up to sigma to the k minus 1 of 1. So let's let a be the minimal number in there. And then we're going to apply the same thing. Right? And so then we get a new cycle that's going to be a, sigma squared of a, up to, let's call it sigma to the L minus 1 of a. So this now would be an L cycle coming from a's. And then we just repeat, always taking new numbers that we haven't used yet, new numbers that haven't appeared in any of the cycles yet. Since 1 through n, this is a finite list, and every time we do this process, we're removing items out of the set. We're removing items to pull out, to use, to build a cycle out of the set. Eventually this ends. So this process ends. And so since when we did the first one, we pulled out k numbers the first time we did it to get the cycle that involves 1. And then we pulled out L new elements to get the L cycle that involves A. And so we keep on doing this until everything has been used up, and then we're done. And so by the way that we've been choosing this, these aren't going to share anything in common because because of the one-to-oneness and onto-ness of our function, we can't have repeats coming in here. Okay, so now let's suppose that we have two cycles, alpha and beta, that don't share anything in common, so these are disjoint cycles. Then these two cycles will commute with each other. What I mean by that is that alpha beta, so this is actually would be beta, apply a beta first and then alpha. This is the same thing as we would get if we do beta alpha. Now it is critically important that these are disjoint cycles for this to be true. If these were not disjoint cycles, then in general this would not be true. So let's just be absolutely clear. The statement is, it's critically important that these are disjoint cycles, that none of the AIs are equal to any of the BJs. So this is because AI is not equal to BJ for any I and J. That these are completely disjoint from each other. Okay, so what is the proof of this? Well, if I take alpha beta and I apply it to, say, AI for one of the i's, well, beta of AI does not appear in there, and so this is just going to be equal to alpha of AI, which is going to give us, spit back out, the next one in the set. So AI plus 1 star, and sort of the star is sort of saying that if we got AK plus 1 is actually A1. Okay. On the other hand, if we applied beta alpha to AI, well then alpha on AI, same as before, we get alpha AI plus 1 star. So we'd have beta on AI plus 1 star, but this doesn't appear anywhere in the B1 through BL, and so beta doesn't do anything to it. And so it's, again, going to be beta plus AI plus 1 star. Similarly, if we did alpha beta on one of the BJs, well, we get alpha would be getting applied to BJ plus 1 star, and BJ plus 1 doesn't appear anywhere inside alpha, and so this is just BJ plus 1, which might possibly just be B1. And last but not, on the other hand, this is the same thing we would get if we did beta alpha onto BJ plus 1, BJ, excuse me. Again, alpha is not going to do anything because BJ doesn't appear in its cycle, and so this is just going to be beta J, and we're done. If we take anything else, so if we have some C that is not inside of the alpha i's and the beta and the BJ's, the AI's and the BJ's, then alpha and beta isn't going to do anything to it. Alpha beta applied to C is going to equal beta alpha applied to C, which is just C. And so we've just gone through and proved that this permutation does the same thing to any choice of numbers. It doesn't matter what order it's in. And so that proves they commute. Okay. So what if we take a single case cycle? We take a permutation that is just one case cycle. well, then the order of that permutation is going to be exactly k. And again, this is pretty easy to figure out because if you look, remember, the whole idea here in this cycle is that A2 is equal to alpha applied to A1. A3 is equal to alpha squared applied to A1. And so down the line, when we get to AK and then apply alpha to AK, well, that's going to give me back A1. But AK was actually alpha applied k minus 1 times to A. And so this is actually saying alpha of k on the A1 gives me back A1. So certainly alpha to the k sends A1 back to itself. Now what about for any other I? Well, alpha to the k applied to AI, well, remember that AI is equal to alpha to the I minus 1 applied to A. And so since we're just applying alpha, really at this point we're just applying alpha k plus I minus 1 times onto A, which is actually equal to alpha A to the I minus 1 applied to alpha k of A1, A1, and alpha to the k, let's write that a little bit better. And so we just saw that alpha k applied to A1 gives me back A1, and so this is alpha I minus 1 applied to A, and then as we just saw before, this gives me back AI. So alpha to the k of AI still gives me back AI. And then lastly, what if we have some C that is not equal to AI for any I? Well, so C does not appear in the cycle. So that means that alpha of C equals C. And so then we have alpha k of C is just, we just get back, keep plugging C back into alpha every time. It's always just going to spit back C. So if we apply alpha k times to anything, we get back with what we started. And so that is k is some number that where alpha has turned into the identity. So we certainly have shown that alpha k is the identity. We also know that it can't be any smaller power than that, because for any smaller power, alpha to the I of A1 is going to give me AI plus 1, and this is going to appear somewhere in the cycle, and so this can't be equal to A1 if I is at least 1 but smaller than k, because this gives me all the other things inside the cycle. So alpha to the k is the identity. Alpha to any smaller power is not the identity. So k is the smallest power of alpha that gives me the identity function. Okay. And then our last theorem for here, which is going to use the last two theorems, is that if we have sigma is broken down into sigma 1, sigma 2, up to sigma m, and these are each disjoint cycles, then the order of sigma is going to be the least common multiple of the orders of each of the cycles. Okay, and we're going to do this by induction. And so our base case, this would be sigma is a single cycle, and so this was proved by the lemma. If sigma is just a single k cycle, well, its order is k, which is just what we proved, and the lowest common multiple of a number is itself. Okay. Now for the induction step, so let's say that we know that the order of sigma 1 up to sigma k is equal to the LCM of their orders. Now we want to find the order of sigma 1, sigma k, and then apply a new disjoint cycle, sigma k plus 1. Okay. And so the important thing here is that these are all disjoint. And so since these are disjoint from what we saw in the previous lemma, these cycles all commute with each other. Okay. And so if I take this and apply it to some power r, then this is equal to sigma 1 to the r, or actually let's keep it grouped together. Since these are commuting with each other, this is going to be sigma 1 up to sigma k to the r times sigma to the k plus 1 to the r. Now, let's suppose that sigma r, let's assume that at some point we have the identity. Well, we only have the identity if both of these individually are the identity, because they don't really share anything in common. Okay? And so if this equals the identity permutation, well, then by what we know with orders, that means that the order of sigma 1 through sigma k has to divide r, and the order of sigma k plus 1 has to divide r as well. And so if they both divide r, that means that the lowest common multiple of the two of them has to divide r. And we know that the order of sigma 1 through sigma k is the LCM of all of those, and so plugging that in here, we get our LCM gets plugged into there, which gives us the LCM of all of them has to divide r. And so what about going the other way? Well, so we need to show that this is the smallest one, and so I'm going to complete this. First, let's clear up some space. So we know that the LCM including the LCM sigma k, including sigma k plus 1 at this point, divides r, where r is the order of sigma 1 to sigma k. Now I'm going to prove it the other direction. Consider taking sigma 1, sigma 2, up to sigma k, including sigma k plus 1, and then raising that to the LCM of all of their orders. Well, since these cycles are all disjoint, they commute with each other, and so I can apply each of this to each of these individually. So it's sigma 1 to this LCM of all of this, all the way down times to sigma k plus 1 to the LCM of all of this junk. Well, note that the order of sigma I is going to divide this LCM of all this stuff, because sigma I is somewhere inside of here, right? And so since it's a least common multiple of something that includes sigma I, that means it must be in a multiple of sigma I. And so in each of these, I'm applying an element to itself, some multiple of its order, and so this is just going to give me the identity times itself, k plus 1 times. And so we just get the identity out of this, and so this is telling me that our LCM divides R, and so since they divide R to each other, they are in fact equal. And that concludes the proof. So let's finish this video off with a quick example. So here is the cycle we started off with at the beginning of the video. So this is a cycle, this is a permutation in S8, and we can see that it is a 3 cycle with 2 cycles, and these are all disjoint, and so they all commute with each other. And so our order here is the LCM of 3 and 2 and 2, and so the lowest common multiple of 3 and 2 is 6, and so we say the order is 6. That is all for this video. We've got a couple more videos at least coming on permutations, and so stay tuned.